if you didn't come to class Monday, Tuesday, Wednesday, if you're having trouble with the homework from those 3 days, watch the video. And then if you still have a question, send me a text or an email. But okay. So this section is exponential models. And if you recall the stock flow diagrams that we had with the feedback loops, and some of them we said grew exponentially. Well, in this section, we're going to look at the exponential models. A stock in a stock flow system is governed by an exponential model. If the net flow into a stock over a given time period is proportional to the level of stock at the beginning. So if it's growing by an even amount each time, like maybe it's growing by 5% or 2 inches per hour, then those can be exponential. The constant proportionality or rate constant is R, and the length of time or time step is T. And this is a little easier to see. Well, I think this example explains it too. But the time step is how often it's growing. One thing that they usually show, other than most of them will be yearly or per hour. But when you're talking about, there's a lot of interest rate problems here. And when you're growing an interest rate, it's usually quarterly, which is 4 times a year, or monthly, 12 times a year. But for most of these, it'll be per year or per, like this one doubles every 20 minutes. So your T is 20. So the time step is how often that increase is. And in this one, it's a doubling. If it were 5% every month, then this would be a month, or if you're talking a year, 12. Looking at this problem, the population of bacteria that we discussed, and it's on page 154 if you wanted to look at it, but that was the E. coli bacteria. Where we had that back loop that kept growing. And it just kept doubling every 20 minutes. There's a net flow of bacteria into the population that is equal to the previous existing population. In other words, there's 100% increase because it's doubling. So if there was 5, then there'd be 10. If there's then 10, 20. It keeps doubling. It's 100% increase. So the rate R is 100%. Written as a decimal, it's 1. And remember that the rate is a pure value. It, other than if you write it as a percent, it does not have units with it. It won't have inches, hours, months. It will not have a unit. It's a percent and can be written as a decimal or a fraction. The most important thing about the rate constant in an exponential model is its sign, positive or negative. If the rate constant is positive, then each increase in the stock will increase the net flow. And this one wasn't an increase because it was positive. So the behavior of the bacteria in example 1 then demonstrates exponential growth, because the more we have here, it keeps doubling, it's increasing it. On the other hand, if the rate constant is negative, then the increase in the stock will reduce the net flow each time. We have stabilizing feedback. That was, if that was a minus, so that maybe you're giving it an antibiotic and it's decreasing. then it would be exponential decay. Example 2 below explains exponential decay. Now, also, if you remember the bathtub where so much was going in and so much was going out, and so we drew the one picture. And it was approaching the 4.8. They call this decay. Even though it's increasing, the amount it's increasing by is decreasing. So even though this is going up, maybe it went up by 20, and then it went up by 18, and then it went up by 16. So the amount it's increasing by is decreasing. This is a decay. So you don't want to just look at the graph. You want to think about what's happening. And each additional minute, it increases it, but it increases by less than the time before. And that's what's making it a decay. Where the bacteria keeps increasing, it's more than the time before. The first time, if there was 5, then it increased by 5. Now there's 10, so it increases by 10. Each time it's increasing by more than the time before. Any questions? Okay, let's look at the other example. Oh. Consider the cooling of a cup of coffee. Over time, the temperature Y of the coffee in the cup will approach the temperature of the outside room. Remember when we said if something's hot, it spreads to the cooler area. And so they're going to say the temperature of the room is P. The rate of heat flow out of the cup is proportional to the temperature difference. Thus, Y minus P is governed by an exponential decay. Decay because the growth out of the cup is the net flow has a negative sign. It's a decreasing. I like the other example better, but your book had this one. But what's happening is it's escaping from the cup. So the cup's temperature is going down, which is negative, and therefore it's a negative flow. A stock in a stock flow system is governed by an offset exponential model. It's just an estimate. If the net flow associated with the stock is proportional to the difference between the level of stock and some constant level or set point. It's easier to understand once we do an example. The biggest thing on this section is knowing it's a growth if your rate is positive. It's a decay if your rate is negative. The bathtub example, oh, I forgot, I put it in here because I like this example better, is governed by an offset exponential model. The set point is the equilibrium, which we said once it hit 4.8, that's where it leveled off. The time step can be taken by minutes, and the water is replaced every 11 minutes. If you go back in your notes, we found that the change in the water, like the water coming in would take 11 minutes for that water to go out. So it refreshes, or the fresh water takes 11 minutes to go out. So the water going in, it's the cycling of the water. That means the rate constant then is 1/11, because we're going in steps of minutes, and every 11 minutes it refreshes the water, but it's a decrease, and that's why it's a negative, because the water's going out. So it's, if you divide that, a negative 0.091. So ratio that they're talking about is this. It's your time step. We're going to go by minutes. And every 11 minutes, it replenishes what was in there. The fresh water goes out. So it's a negative 1/11. Or negative. Now your book puts a 2 here. They like to do this extra rounding. I'm not sure if they're doing that because of error or, but it should round to 0.091, not a 2. If we look at the picture. Oh, this is the one that I showed you. This one. If you go to page 152, figure 18, it's this one. It shows the exponential decay of the water level, and the set point was 4.8. But to find this rate of constant, it's just whatever your time step is. So if something's compounded monthly, it would be monthly, it'd be a 12. And divided by how long it takes to replenish. The residual formula that we had, that's how they got the 11, or we got the 11. Now in these problems, most of those will be given, you won't have to find them. Okay, let's find a formula. To find a formula, so then it's a lot easier than trying to do it all in your head, or not know where to start. Suppose we begin with 1 bacteria of E. coli, and from before, we know it doubles every 20 minutes. How many bacteria cells should we expect after 2 hours? Assume exponential growth. So we are assuming exponential growth because it's doubling every 20 minutes. So for the first time when it starts, we have 1 bacteria. In 20 minutes, how many bacteria are there? Anyone?
2.
If it doubles, there's
2.
2. In 40 minutes, 20 more minutes, this will double again. And then another 20 minutes, 4 becomes 8. In 20 more minutes, 8 becomes 16. 32, 64. Any questions on that part?
What page is this on in the book?
Okay, not looking at this first one. If we look at this, this is 2 to the first. That was 1 set. The next one is 2 squared. Because each time we're taking this value and multiplying by 2. So the next one is 2 cubed. 2 to the 4th. Any questions? I don't know. I don't know if they have this in the book. Let me see. It would be in 6.4. or I mean, wait, we're on 3.4, sorry. It would be in 3.4, so this whole section is 3.4. Right here. So it is on page 166.
Thank you.
And they're showing you how it's doubling. And then in words, they try and explain the equation, but I think it's easier to look at it through a chart. This first one, notice we're going 1, 2, 3, 4, 5, 6. The first one is 0. That's our starting point. Notice 2 to the 0, if you plug that in your calculator, it's 1. Anything to the 0 power is 1. So our formula could be 2 to the x. Now, the reason they're saying, like they did over here, they divided by how many times it repeated or when everything refreshed. So this would be dividing by 20. If we use just x, then it's how many sets of 20 are you talking about? Like this is the first set of 20. This is after 2 sets of 20 or 40 minutes. This is after 3 sets of 20. If you're just using an X, then you got to think about that. It's talking about how many times does it double, not minutes. So written just like this, would be this. Now, if we wanted to do it the other way, we need a lowercase t and an uppercase t. In this case, t is the number of minutes, and the capital T is time to, in this case, double, which is 20 minutes. So it depends on which way you want to think about it. If you're thinking about how many times it's doubling, you can use this one. For this problem, it might be easier to put the time. So then our formula would be t divided by 20, because we know our doubling time is 20 minutes. So then if we just put the total time here, notice for this last one, 120. 120 divided by 20 is 6, and 2 to the 6th is 64. Okay. Two different versions I'm going to show you on the next page of the formula, and it's up to you which one you would want to use. Also notice this is a 2. We said it was doubling by 100% or a 1. Well, there's what's called a 1 plus trick, and that's why it's a 2. Because anytime you're increasing by a rate, you can use a 1 plus trick. In this problem of doubling, oh, it's on the next page before. Our R was 1, and that's where they're getting that too. So that's how we got the 2. Starting with E. coli bacteria, how many does the exponential model predict after 24 hours? We'll use this formula. But T is minutes. And they gave us hours. So we first have to convert that to minutes. One hour is 60 minutes. Now, was I right in putting the 1 hour in the denominator? I was right, because I want the hours to cancel. $24 times 60 is 1,440 minutes. T was in minutes, so I can plug that in now. Now you can enter this into your calculator. 2 caret parenthesis 144. Like that. I'm gonna go 1 decimal place. I don't need all these values. 4.7 times 10 to the 21. That's pretty big. In 24, so in 1 day. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So there'd be 4.7 times 10 to the 21 bacteria in 24 hours. If it doubled every 20 minutes. Any questions on that? Positive. I thought this was kind of interesting. It's in your book. It's a French riddle for children, and it also illustrates exponential growth. Suppose you own a pond which a water lily is growing. The lily plant doubles in size every day. If the lily were allowed to grow unchecked, it would completely cover the pond in 30 days. So it doubles every day. Choking off other forms of life in the water. For a long time, the lily plant seems small. And so you decide not to worry about cutting it back until it covers half the pond. On what day will that be? So you have a pond. And there's a nice little lily in it. And every day it doubles. When will it cover half of the pond if it takes 30 days to completely cover it? Every day it's doubling. So the first day, now there's twice as large. Now it will be 4 of those.
Is it 15 days?
Remember, if it's doubling every time, once it reaches half of the pond, the next day it's going to completely cover it. So what seemed small at first, doubling, once it covers this whole side of the pond, the next day it's going to double and cover the whole pond. So if it takes 30 days for the whole pond, it's on the 29th day, it will be covering half of the pond. Because then the next day it's going to double and cover the whole pond. So what seems to be small, growing and doubling, all of a sudden it's so large that when it doubles, this kind of shows you how big it jumps. Just like the chart we were looking at, it was 2 and then 4, then 8, then 16. So in 2 hours, there was only 64, whereas in one day, there was 4.7 times 10 to the 21. And so that little doubling all of a sudden jumps. Any questions on that? Here's where it gives you the two formulas. Suppose the stock S is governed by an exponential process with time step t and the rate constant r. If S sub 0, that's the starting amount, is the initial value of the stock, and S sub n is the stock at any certain time, then you can use this formula where S sub 0 is the starting amount times 1 plus your rate, and then to the n power. N is the number of time, the total compoundings. So in our 20-minute one, it was how many 20-minute cycles there were. Or you can use this one where however many times, like the 20 minutes is on the bottom and total minutes is on the top. Both get you the same thing, just depends on your thought process. Okay, let's look at this example. Grandparents decide to deposit $5,000 in a college fund. So I like to underline important areas. In a college fund when the grandchild is born. They earn 0.2% interest each quarter. Determine the number of, determine the time step and the rate constant, and then use the law of exponentials to estimate the value when he turns 18. Now it depends on which one of these two equations you want to use. Is there a preference? I like this one. So I will show you this, but then if you want to use this, let me know. But if we use the top one, we know S of O, that's our starting amount, 5,000. And then we know the rate 2%, 0.2. When you are plugging R in, you need the decimal. Divided by 100, move the decimal to the left 2. Now, if you're, oops, let me write that in there first. If you're using N, N is total compounding. It's compounded quarterly. Quarterly means 4 times a year. So it's the number of compounding in 1 year times the number of years. This would be our formula. And N, we wanted to know when the child turns 18. Is there any questions on the equation? The number of compoundings is 4 times the number of years, which was 18. So N is the number of times it will be compounded. It's the number of quarters. Any questions on that? Now this S sub N, we're plugging in 72. So that lets you know how many compoundings you're talking about. That way, if you find different values, then you have all of them. And then just plug that into your calculator. So the formula, starting amount, your rate, and then N is the total number of times it's compounded. In this case, it was quarterly, so that's 4 times a year. And we're doing it for 18 years. When you plug that into your calculator, you should get $5,773.59. Now, it seems like it was in there a long time, but I mean, you weren't even making a whole percent. And right now, interest rates are pretty low. Any questions on that? Historically, looking at number 4, historically, investment in stocks has yielded an annual return of 7%, but with considerable variability. Suppose the grandparents instead put $5,000 in a stock fund that earned exactly 7% each year for 18 years. How much will be in the account at the end? So we're doing the exact same problem, except instead of 0.2, we want to see what 7% will do. So it's basically the same equation, except R. We're starting with 5,000. 1 plus your rate. to the n. Now our rate in this one is 7%. What is 7% written as a decimal? Yes, 0.07. And this was S sub 0 because that's our starting amount. N will be the same because it's still compounded. I believe they wanted to keep it the same. Well, no, this is different. In a stock fund that earned exactly 7% each year. So instead of quarterly, this one was 0.2% quarterly. This one is 7% each year. So N would be each year. So once a year, 18 years. So it's 18. So it did not say quarterly. Or if it did, I didn't write it. So we'll go with what I wrote. But this one says 7% a year. So you do have to be careful of units. This one said a quarter. So this is going 4 times a year. But it's still 7% is still pretty large. I think you'll still make a lot more here. Beginning $16,899.66. Any questions on that? So always be careful of the units. This one was in years, the other one said quarterly. Any questions? Let's try the homework then, because the homework will be similar to that. Okay, so if we look at Friday's attendance problem, it says, let me shrink this a little. Oh gosh. There we go. Phosphate rock is primary source of phosphorus fertilizers in agriculture. Mining of phosphate rock has grown at an average of 3% per year. So that's what we're growing by. Most of the last century. And 160 million metric tons of phosphate rock were mined in 2010. If the mining of phosphate rock were to continue at the 3% per year, approximately what quantity would be mined in 2050? So each year we're increasing by 3%, which means it's a growth. And go with what you're starting with. So remember your formula is S sub 0 times 1 plus R to the N. I'm getting a very large number. Oh, in the millions. You should be getting around 522 million. If we start with the starting amount, so we're starting in 2010. Because we know how much was in 20, that's not a percent. So S sub 0 is our 160 million. R is the rate at which it's growing, and it's growing positive 3%. So what value do we put in for R? Remember, make it a decimal. What's 3% as a decimal? Yep, 0.03. So that would be our equation. Now this value was in 2010. It's growing by 3% each year. And we want to know how much in 2050. If N is the number of years, because it's 3% per year, from 210 to 250, how many years is that?
40,
Anyone?
40,
It would be 40 years. Because if we're going from 10 to 10 and we add 40 years, it would be 250. So this has been increasing by 3% a year for 40 years. So then you would just put 40 in. And then just plug that into your calculator. Any questions on it? I hate that box. So everyone, I rounded 3 places, so I got 522 million. Is that what everyone's getting? $1,000. So 522 million metric tons. Any questions on that?